Hi, in this video we're gonna work on the integral test and p-series test. So in class last time we saw how if you have the summation of n equals 1 to infinity of 1 over n, we saw that this is called the harmonic series which diverges. And I showed you in class why it diverges. So we're going to say this diverges. And so now I want to know, what about n equals 1 to infinity of 1 over n squared? What does this do? Does this converge or diverge? Now, one of the things to remember is the divergence theorem. The divergence theorem tells us if the limit is not 0, then we know it diverges. Now, if the limit as n goes to infinity of a sub n is 0, like in both of these, notice that one as n goes to infinity, 1 over n goes to 0, but we know that that diverges. So if the limit as n goes to infinity of a sub n is 0, what I want you to remember is that that means we know nothing. It does not converge, it does not diverge. We just don't know yet. We have to use a different test. And so here I'm going to informally use what we are going to learn in a little bit, which is the integral test. So if you remember when we did improper integrals, if I look at the integral from 1 to infinity of 1 over x squared dx, right? I changed my n to x. We saw that this integral is negative 1 over x from 1 to infinity. And as x goes to infinity, you end up with 0 minus a negative 1, which is 1. So in this case, we will say the integral converges. And the integral, if you look at that series, so we're going to compare what do the terms look like. But this integral essentially approximates the series. So we can say then, since the integral converges, then the series will converge as well. Converges, since the integral converges. Now, in order for us to say that, we have to be a little more careful and be able to specify the conditions of the integral test. But before I get to the integral test, so far we know that if I have n equals 1 to infinity of 1 over n, I know this diverges. And the integral from n equals 1 to infinity of 1 over n squared, this converges. So the big question then is, well, first let me ask you, what if I have two series and you know one of them converges and the other one diverges? So here are the two. Maybe. If I say n equals 1 to infinity of 1 over the cube root of n versus the summation n equals 1 to infinity of, say, 1 over n to the fourth. Which one do you think is going to converge? Right, and you can think of this as this is 1 over n to the 1/3. And so based on what we did on our work with improper integrals, notice that this is the one that converges. When we did improper integrals, we looked at the integral from 1 to infinity of 1 over x to the fourth. And if you do this integral, notice that you're going to get negative, what's this, negative 1 over x cubed and then 3 from 1 to infinity. So as x goes to infinity, this is going to go to 0. So you end up with 0 minus a minus, so plus 1/3. So it converges. The integral converges, which means the series will converge as well. And so this brings us to the P series. So a P series is a series of the form n equals 1 to infinity of 1 over n to the p. And this converges just as before with improper integrals. It converges when p is greater than 1, and it diverges when p is less than or equal to 1. So that's what a p series is. So you essentially, which comes from the integral test. So let's talk about the integral test because we have to talk about the conditions. Why is all of these above working? So we're going to look at the integral test. So let's consider the same series above. Consider the series the 1 over n squared. Now, if you look at the terms of this series, right, this series, if we start listing some of them, the first term is 1 plus, you're going to have 1 over 2 squared, so 4 plus 1 over 3 squared, 9, and so on and so forth. And it keeps going, plus 1 over n squared, and it goes on to infinity. Now, when we look at the integral, right, the integral of from 1 to infinity of 1 over x squared dx. Now, just on 1 to infinity, let's look at the graph of that. So I am looking at, let's see, 1 over x squared, and I'm only looking from 1 to infinity, so we're strictly staying in quadrant 1. So is this one. 1 over x squared, the other half is on the other side, but we don't care about that since we're just going from 1 to infinity. So at 1, if I do a left endpoint, the height of this rectangle is given by 1 over 1 squared. So this is just 1, 1. And then as we move on to the next one, so notice that this is a1 equals 1. And then as I move on to the next rectangle, the height of that is a2 equals 1/4. And the next rectangle is a3 equals 1/9. So notice that we are essentially getting the terms of the series. So when I'm using the left endpoint, am I getting an over approximation or an under approximation? I am getting an over approximation with the left endpoint. So this is an over approximation. And so notice that the integral is the area under the curve, right? If you look at the curve exactly, the area under the curve is the integral. Now the series is above it. So the series is slightly larger. But now let's look at the same 1 over x squared. So I'm still looking at the same, but what if I do an right endpoint? So that means when I'm at 1, 2, to get a right endpoint, right? Notice that it's because I'm going from 1 to infinity, I really can't use the right endpoint of 1 because I can't draw a rectangle over to the y-axis. So my first rectangle actually starts at 2, and then I go this way, which is really then A2, because the area of this guy is 1/4, or the height, sorry. Well, the area, since the length is 1. So I'm really starting with A2. And then at 3, we're going to go over here. So this is really A3, which is 1/9, and so forth. When n is 4, you're going to go A4, and A4 is 1/16, and we just kind of keep going like this. So from these two pictures, let me call them picture A and picture B. One of the things that you can notice is that the series is squeezed between these two. And what I mean by that is my A1 plus A2 plus A3 plus dot 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 plus, we're going to say A sub n, is between the integral from 1 to my last one here, right, is going to be n. So this is my A sub n. So, and this is n plus 1. So it's going to go from 1 to n plus 1 of f of x dx. And this one, it starts at, so if I wanted to use from 1 to n, I need to take in, I'm missing the first term. So it's going to be 1, right? The first term of my series is, it's over here, 1. So I need to put that 1 in here, plus the integral from 1 to n of f of x dx. And because now I'm taking all that into account. And this guy is my s sub n. So with these two formulas now, we can approximate the sum. And notice that as long as my function is decreasing, I'm going to be able to do this. So for the integral test, we have to have a function of positive values, continuous, and decreasing. Notice that this has to be decreasing in order for us to be able to make this inequalities. So if my function was not decreasing, right, if I was increasing, I can't say this. So my sum, so the integral from n plus 1 of f of x dx is less than or equal to essentially the sum. N equals 1 to n, whoops, let me call that a k. K equals 1 to n of 1 over n squared, less or equal to 1 plus the integral from 1 to n of f of x dx. And this should really be a k squared. K squared. As n goes to infinity, then you end up getting the integral and the sum. The sum is squeezed between this over approximation and that under approximation. And so if the integral converges, the series has to converge. So we're kind of using the squeeze theorem here as well. So as n goes to infinity, we can use the squeeze theorem to show that this series will converge. If the integral converges, then the series converges as well. Of a sub n. So this is if f of x is equal to a sub n, then this series converges. And if the integral diverges, then what do you think the series is going to do? The series diverges as well. So that is the integral test, right? If the integral from 1 to infinity of f of x dx diverges, and f of x is a sub n, then the series diverges as well. So that's the integral test. So the conditions of the integral test are three things have to happen. So you have to have positive terms of a sub n, f of x equals a sub n, or a sub x, really, a sub n. A is continuous, and f of x has to be decreasing. So if these three things happen, then we can use the integral test. As long as these three conditions are met, then we can say if the integral converges, then the series converges. And if the integral diverges, the series diverges. And the reason that it has to be decreasing again is because of this under and over approximation inequality that we did over here. And I know that this may be a little bit hard to kind of visualize, but if you go back and kind of pause at this video and really look at what's going on here. So here you're starting at a sub 1, so the 1 is included, and then a sub 2, a sub 3, a sub 4, all the way to a sub n. So, and the integral is from 1 to n plus 1. So if I go a little bit over, it's smaller than, right, the sum, because the sum is an over approximation of the integral. So then the integral is smaller than the sum. But then when you look at it over here, the starting at with a sub 2, this is an under approximation. So the sum is less than the integral from 1 to infinity, but we need to include that extra term here, or first term. And then as n goes to infinity, by the squeeze theorem, we can say these are going to behave the same. So when can you use the integral test? You have to make sure it satisfies all those things. So series where you can use the integral test will be, an example is the summation n equals, say, 3 to infinity of the natural log of n over n. Right, so notice that if I try to do the divergence test for this, first I always take the limit as n goes to infinity, ln of n over n. Which one grows faster by growth rate? N grows faster than natural log, so this is going to go to 0. So if the limit is 0, again, it means we know nothing. So you have to use another test. So you usually want to check to see if it's geometric or if it's p-series, but it's none of those. The fact that the derivative of natural log of n is 1 over n lets me know, oh, I can use the integral test. Let f of x equals ln x over x and find the integral from 3 to infinity of ln x over x dx. But first, make sure that this is continuous on 3 to infinity, positive terms, which it is, and decreasing. So for the decreasing is where we have to work. So we either have to use